Okay, let's go through paper 6, which is the alternative to the practical. This is for chemistry from Cambridge IGCSE, Cambridge International Examinations at CIE, and from May-June 2016, and the code is 0620/61. All right, let's get started.
Time for school, time for school, time for school, time for school. All right, I'm up. It's time for school. Whoa!
Question 1. The diagram shows the apparatus used to separate a mixture of water with a boiling point of 100 degrees Celsius and ethanol with a boiling point of 78 degrees Celsius. Okay, so this is the apparatus. We have a mixture here being heated, and that's the water and ethanol, and it evaporates, moves up this column here. There's a thermometer up here. Then it condenses down into the condenser, and it's collected down here into this solution. And at different temperatures, they'll know which one it is that's coming out. All right, because the one that boils will be the one that has the boiling point matching whatever it says on the thermometer. Okay. A. Complete the boxes to name the apparatus. Okay, so first of all, here we have a two-dimensional drawing of a tripod. You can only see 2 legs, but it's a 3-legged stand. Okay, and this here, up the top, the second box, that is called a fractionating column. A fractionating column. So you can collect the different fractions at the different boiling points. B. Label the arrows on the condenser. Okay, so what we have here, we have water goes in. It's cold water. Water goes in, and it goes up, and there's nothing else. It can't react. It's going around the outside of the tube, so its water comes out. Nothing else can come out. There we go. C. Identify one mistake in the apparatus. Well, there is one big mistake. Let's look at this. All right. It doesn't say what sort of heat here is used. It's implying it's a Bunsen burner, but it doesn't say it's a Bunsen burner. It's just being heated. Okay, so we can't say that that's a mistake. It's a safety thing that you don't use a Bunsen burner with alcohol, but it's not a mistake. Okay. It has bungs where it should have. It has a thermometer in. Comes down. Water's going in the bottom and out the top as it should. Everything's good. It's being collected in the beaker. But then why is the beaker being heated? There's no reason for the beaker to be heated. So that is a mistake. Because what you're going to get is all the stuff you've just worked so hard to collect evaporating off. So the answer to this is that there's heat under the collecting beaker. No need for it at all. It's a silly idea. D. Which liquid would collect first? So would it be water with a boiling point of 100 degrees Celsius? Or would it be ethanol with a boiling point of 78 degrees Celsius? Well, ethanol would boil first, so that's the one that would be collected first. So ethanol, because it has a lower boiling point. And E, why would it be better to use an electrical heater instead of a Bunsen burner to heat the water and ethanol mixture? The key word there is ethanol. Ethanol is flammable. Bunsen burners use flames. And electrical heaters just create heat from electricity. So it's because ethanol is flammable. Ethanol is flammable. There we go. Question 2. 2. A student investigated the reaction between aqueous sodium carbonate and 2 different solutions of dilute hydrochloric acid, acid A and acid B. The reaction is sodium carbonate plus hydrochloric acid produces sodium chloride plus water plus carbon dioxide. That makes sense because, first of all, we have an acid plus a carbonate produces salt plus water plus carbon dioxide. That's one of the reactions you should know. A. Experiment 1. Using a measuring cylinder, 25 centimeters cubed of aqueous sodium carbonate was poured into a conical flask. Thymol-phthalate indicator was added to the conical flask. A burette was filled up to the 0 centimeters cubed mark with a solution A, or acid A, of dilute hydrochloric acid. A was added to the flask until the solution just changed color. So this is a titration. This is a normal titration. You need to know how to do titrations because chemists love titrations. It comes up all the time. Use the burette diagram to record the reading in the table. Okay, so it started off at 0.0 centimeters cubed, as it says up here, and it ended off at this value. So this is, if you look at this, we have 12, 13, we have 10 gradations, so each gradation goes down 0.1. Okay, so this is 13.2 centimeters cubed. Okay, now there's a table that we have to record this information in. All right, here we go. So it says final burette reading first. So that's 13.2 centimeters cubed. Oh, but it says centimeters cubed here, so you do not write it here. That's an important point because you never ever write the units in the cells of a table. You will lose a mark. Okay, 13.2, and it started off at 0 centimeters cubed. If you write that down, you'll lose a mark because you have to have it to the same number of decimal places. 0.0, it even says in the question that it started at 0.0. So the difference is obviously 13.2 centimeters cubed. That should be straightforward. Experiment 2. Experiment 1 was repeated using methyl orange indicator instead of thymolphthalein. Methyl orange is red-orange in acidic solutions and yellow in alkaline solutions. This may come up later, red-orange in acidic solutions and yellow in alkaline solutions. Okay, use a burette diagrams to record the readings in the table and complete the table. All right, so it started off at 12.5678. Okay, so it started off, the initial reading was 12.8 centimeters cubed. The final reading was 39.2 centimeters cubed. It seems silly that they always put final before initial, but that's for subtracting purposes. It's not because it makes it easier, because it's a very common mistake that you just write the initial in the first box and the final in the second box, and then you lose a mark, because clearly that's not what it says it is. Okay, so then you take 39.2 minus 12.8, and you get 26.4 centimeters cubed. There we go, 4 whole marks there. B. What color change was observed in the flask in experiment 2? Okay, so in experiment 2, as we said, they used methyl orange instead of thymolphthalein, and they started red-orange in acidic solutions and yellow in alkaline. So if you remember, it started off with, in the little flask, they put in their alkali solution, sodium carbonate, and then they dripped in their acid. That's their little drip. So it starts off as alkali, yellow in alkaline solutions. And it's red-orange in acidic solutions. There we go. So it turns a red-orange, or it's only slightly, it's only just barely started to change color, so you could say pink. But a red-orange or pink. Okay, so it started off yellow. And I'm going to say it went to orange, because red-orange is just kind of like a brighter orange. Okay, so you could say red-orange, you could say pink, or you could say orange, or you could say red, because you're not given what exactly it is the exact color it changes to initially. If you go too far, it will be red-orange. C. Experiment 3. Experiment 1 was repeated using solution B of acid instead of solution A. Use a burette diagrams to record the readings in the table and complete the table. So that's 6 marks for being able to read some burettes. So you have to know how to read burettes. Okay, so the initial burette reading, that would be 9.9 centimeters cubed. And the final burette reading would be 16.5 centimeters cubed. And if you subtract 9.9 from 16.5, you should get 6.6 centimeters cubed. That's another 2 marks for reading your burettes. D. Suggest one observation other than color change that is made when hydrochloric acid is added to sodium carbonate. Keywords there, we have acid and a carbonate. What do you get? You get carbon dioxide, which is a gas which bubbles. All right, so nice word that is really good that they like to, I like to see it. I think it sounds much nicer. Is effervescence. But you could also say bubbles or fizzing. That works as well. You cannot say a gas is given off because you are observing. Suggest one observation. Observation is something you see, you smell, you hear, something like that. It's not something you know. You know it is a gas. You can see it is bubbles, but you know it's a gas. So the observation is that it has bubbles. The explanation is that it's a gas, specifically carbon dioxide gas. Okay, so be very careful. They like to put questions like that in. E. Complete the sentence below. Experiment, which one, needed the largest volume of hydrochloric acid to change the color of the indicator? So which one needed? Let's go look at which experiment. So experiment 1 needed 13.2 centimeters cubed. Experiment 2 needed 26.4 centimeters cubed. And experiment 3 needed 6.6 centimeters cubed. I think the biggest one there is experiment 2. There we go. That's it. F. What would be a more accurate method of measuring the volume of the aqueous sodium carbonate? So remember, it said they used a measuring cylinder. So a measuring cylinder isn't as accurate because the diameter, this is my beautiful measure, I'm terrible at drawing on this thing, sorry. The diameter of the measuring cylinder, that's our little gradations along the side, is wide. Okay, so it's much less accurate than if you used a pipette or a burette because the diameter is much narrower. You still have your gradations, but it's much narrower. So that makes it much more accurate. So you can use a pipette or a burette. Both work quite well because their diameter of the tube is much more narrow. So they can be more accurate. G. What would be the effect of the results, if any, if the solutions of sodium carbonate were warmed before adding the hydrochloric acid? Give a reason for your answer. Okay. Looking at this equation, as we said before, we have sodium carbonate plus hydrochloric acid produces sodium chloride plus water plus carbon dioxide. So they want to know what would happen if sodium carbonate was warm. They're not saying anything about the speed of the reaction. What they're talking about is the effect on the results, and the results are the volume of hydrochloric acid needed to neutralize the sodium carbonate. And the volume is not to do with temperature. The volume is to do with the mole ratio, 2 to 1. Okay, so it will go faster if it's warmer, but it won't affect how much gas is produced in the end. So the effect on results, none. And the reason, it doesn't change the concentration of either the acid or the alkali. Heating doesn't change the concentration. It just makes the reaction maybe happen faster. H1. Determine the ratio of volumes of dilute hydrochloric acid used in experiments 1 and 3. Okay, let's look at the answers. In experiment 1, we used 13.2 centimeters cubed. And experiment 3, we used 6.6 centimeters cubed. So we have 13.2 to 6.6. Divide each of them by 6.6. And we have that equals 2 to 1. Okay, it doesn't want you to show you're working. That's just so you know how it works out. So the ratio is 2 to 1. Make sure you do it in the same order it says here. Experiment 1 to experiment 3. Okay, So experiment 1 to experiment 3. It's not a 1-to-3 ratio, it's a 2-to-1 ratio. H2. Use your answer to H1 to deduce how the concentration of solution A differs from that of solution B. Okay, so how is solution A different to solution B? Well, solution B is double the concentration, and the reason why is because it took twice as much of the acid to neutralize the alkali for experiment 1 than it did for experiment 3. So acid B is double the concentration of acid A because this experiment used acid A, this experiment used acid B. Okay. I. Suggest a different method using standard laboratory chemicals to determine which of the solutions of dilute hydrochloric acid, A or B, is more concentrated. Okay, the different method means it can't be anything like a titration. Okay, so you're not doing a titration. You need another way of finding how concentrated the two acids are. Okay, there's a few things you can use. Well, the marks you get for this, 1 mark is for writing down the method. 1 mark is for writing down the reagents you use, and 1 mark is for writing down the results you would see. Okay, that's why it's a 3-mark question. I'm not sure how you can quite fit it on these few lines, but okay. Okay, so first of all, when you're looking at this, think about what are some of the reactions you need to know for acids. Okay, acid plus a carbonate, acid plus a metal, any of those sorts of things. I'm going to choose an acid plus a metal. All right, acid plus metal, salt, water, hydrogen. All right, okay. So first of all, I'm going to place the same amount, and I'm going to say 50 centimeters cubed of acid A and acid B into separate beakers. Why 50 centimeters cubed? Well, you're describing a method, and you just should choose a value that you're putting in. There's no right or wrong answer about how much you choose. Okay, you could say 100, you could say 200, you could say 500, you could say 20, it doesn't matter. So add a 3-gram strip of magnesium. Again, I'm just randomly choosing a number out of thin air, so it doesn't matter how much you use, to each beaker, and time for 3 minutes. You could just say, see how long it takes for the magnesium to disappear, but I'm just going to say time it for 3 minutes. So remove both strips from the acid, wash and dry them off. Okay, so it's still continuing to react with the acid. Okay, then you weigh them. So weigh each strip to find which reacted most. And finally, the lightest strip was in the strongest acid. Okay, there's other methods you could use. Basically, they're fine with pretty much any method as long as it showed that you know what typical reactions are for acids and can you design a little bit of an experiment. Question 3. 2 substances, C and D, were analyzed. Solid C was a salt and solution D was an aqueous solution of chromium-3 chloride. So C was unknown and D was chromium-3 chloride. The tests on solid C and some of the observations are in the following table. Okay, tests on solid C. So solid C was added to distilled water in a test tube and shaken to dissolve. The solution was divided into 2 portions in test tubes, and the following tests were carried out. So first of all, they looked at the appearance of the solution. It was colorless. There are many things that are colorless. It's probably not a transition metal, though. And the pH of the first portion of the solution was tested, and that was pH 7. So it wasn't an acid, it wasn't an alkali. All right, keep going. There's not a huge amount of information they've already given you. So let's see what we can get here. Dilute nitric acid was added to the second portion of the solution, followed by aqueous silver nitrate. Aha! With this one, remember, it tests for chloride ion, gives a white precipitate. The iodide ion gives a yellow precipitate. And the bromide ion gives a cream precipitate. As this is a cream precipitate, it is bromide. Okay, and a flame test was carried out on solid C. Yellow flame color means it's sodium. So identify solid C. It is sodium bromide. There we go. And B, describe the appearance of solution D. And if you remember, solution D was chromium 3 chloride. Now, chromium 3 chloride is a transition metal. Chromium is green. All right. C, tests were carried out on solution D. Complete the observation for tests 1, 2, and 3. So 1, test 1. Drops of aqueous sodium hydroxide were added to solution D. Excess aqueous sodium hydroxide was then added to the mixture. Okay, so when you add the sodium hydroxide, a little bit of sodium hydroxide to chromium, you get a green precipitate. So you get a green precipitate initially when you added drops of sodium hydroxide. Then they added excess aqueous sodium hydroxide. Okay, when they added the excess, that precipitate dissolved, and you just got a green solution. Okay, so a green precipitate initially, and then it became a green solution when it was in excess sodium hydroxide because the precipitate is soluble. All right. 2. Test 2. Excess aqueous ammonia was added to solution D. What do you see? What are your observations? Okay, so when you add ammonia to chromium, you get a gray-green precipitate. So a gray-green precipitate. And 3, in test 3, dilute nitric acid was added to solution D, followed by aqueous silver nitrate. That's the same test as before, where the chloride ions, that was white precipitate. The bromide ions, that is cream precipitate. And the iodide ions, that's a yellow precipitate. So what do you see? Remember, this was chromium 3 chloride, so you would get a white precipitate. All right, and then D. Chromium 3 can be converted to chromium 6. Chromium 6 is hazardous. Suggest 1 safety precaution when using chromium 6. Okay, so chromium 6, I would say wear goggles. You don't want to have anything hazardous go into your eyes. You could also say use a fume cupboard or wear gloves. Any of those would be okay. You don't, it just says chromium 6 is hazardous. It doesn't say it's a hazardous gas, but fume cupboard, gloves, or goggles all work well. Question 4. Calcium burns in air to form calcium oxide. The reaction is vigorous and some of the calcium oxide can be lost as smoke. Plan an investigation to determine the maximum mass of oxygen that combines to form calcium oxide when 2 grams of calcium granules are burnt in air. You're provided with common laboratory apparatus and calcium granules. Okay, so basically you're mixing calcium plus oxygen produces calcium oxide. And to balance that out, we have 2 and 2. You don't need to put in this equation. That's just to say what's happening. So you're burning calcium, and if you just burn it in air, it will react with the oxygen in the air, and you'll get calcium oxide. That's what they're saying. Okay, you don't need to write this. As I said, you do not need to write this equation in. That's just for your benefit. Okay, so they left this blank spot. It doesn't say that you need to draw the apparatus. It doesn't say anywhere about drawing the apparatus. And there's no marks for drawing the apparatus. So while this is here, you don't need to actually use it. You can if you want, but you don't need to. You could use this for planning it out. I would actually use another page, write out your plan of what you're going to do, and then draw a line through it so that the examiner knows that that's just your rough work. But for this question, I would always plan out your experiment on a separate piece of paper first before you start writing anything down, because quite often you need to get things in the right order. And if you have lots of arrows saying, oh, this should go before here, then it gets messy. If the examiner can't find the marks, they can't give you the marks. So what we're doing here is we're burning the calcium in a crucible, and we lift the lid so that it will react with oxygen, and we cool it and weigh it, and we reheat it until it's the same weight. It doesn't change weight when next time we weigh it. And basically your final observation is you calculate the difference in the initial weight and the final weight. So let's write that down. So weigh the calcium in the crucible with the lid. And remember, a crucible is really a little ceramic dish that you can heat really, really high, and it has a lid that sometimes is on top, or sometimes for other reactions you don't need to. But it's just a ceramic dish that you can heat really, really strongly. Okay, then you heat the calcium. You could also say burn the calcium. Either okay, because it says it's burning in oxygen. So allow air to enter by lifting the lid. So let cool and reweigh the calcium oxide. So remember, it was initially just calcium that you put in the bottom of this crucible. By burning it and then lifting the lid, it changed into calcium oxide. So you reheat it until the mass is constant. So basically you reheat it as long as you think it's needed, then you let it cool again, you reweigh it, and hopefully it'll be about the same as it was last time. If not, then you're going to have to reheat it again. So calculate the difference in initial and final masses to find the mass of the oxygen. So whatever the difference is, that will be because of the oxygen. All right, so this is 6 points for 6 marks. That's good. So you said something about the method you'd use. You've said about the results that you're looking for, and these are important. Okay, and always double check once you've finished writing everything. Double check to make sure that you've answered the question. So this is to plan an investigation to determine the maximum mass of oxygen that combines to form calcium oxide. So you're weighing out the calcium oxide at the end. That's what you're trying to find. So you need to state how you're going to get this final result. All right. And that's it. That's the end of this question, and that's the end of this exam. I really hope you found this useful. I hope that you'll do very well on your exams. And if you do like this video, please press the thumbs up button. And if you haven't subscribed already, we'd really appreciate it if you did. If you have anything you'd like to say to us, please write them in the discussion section below, and have a great day.